So, in this module let us understand generalized RBF networks and study this as part of our course. So, you may wonder at this point, by seeing the architectural sketch of the Green's function based regulation network, that for every data sample xi I need to have a Green's function unit g of x comma xi associated with it. In practical problems, the data set can be quite huge, humongous, right. So, I may have like a million data points or 10 million data points, and if I were to devise this network, then I would I would need to have maybe a million or 10 million nodes in the hidden layer, where each node acts as this Green's function unit, and this can be really prohibitive, right. So, we want to restrict that size somehow, and that is part of our study. So, what if we impose these conditions, how would the network behave, and then in lieu of this how would we solve for our optimum weights. So, let us see this in this context. Okay. So, let me write this up. The one to one correspondence of a training sample xi and an associated Green's function g of x comma xi can pose many problems, particularly computational problems that involve both both memory and computation, both, right. I mean I would say computing problems that involves both computational side, that is evaluations, and then memory as well. First, it can be a prohibitively expensive network when n becomes large. Second, for determining the unknown coefficients or weights from the hidden to the output layer, we need to solve a linear matrix equation, and in the process of solving this matrix equation we require inversion of this matrix, which is on the order of n cube, where your matrix is of size n by n. Therefore, this is quite complex, it is prohibitive. In addition, there can be ill conditioning on the matrix. This is an important detail as well, right. You have a solution like Ax equals b, right, where x is like your weight vector and b is like your desired response. To solve for x you have to do A inverse b, and this inversion can be an issue. So, if the matrix is really large, then inverting this becomes a problem, But even if you can invert, right, sometimes you may not be able to invert because there it could be ill conditioned depending upon how you form this matrix, right, depending on the data. It can be ill conditioned. This requires special handling. So therefore we need additional regularization here. Okay, let us see this within this context. So what we require is as follows. We need an approximation of the regularized solution. So what it means is, this is the idea that we have. We would want to approximate the regularized solution in a lower dimensional space using possibly a suboptimal solution. What this means is I want f star of x expressed as a linear combination of my basis, which is a new set of basis which is given by phi I acting on x. It is a linear combination, but I have a far fewer set of bases in an M1 dimensional space where I am approximating this function, right. If you just recall, my original f of x was done using all the training samples, where for every training sample I had an associated Green's function, but that is prohibitively complex. Plus when you solve the when you get the Graham matrix and then you formulate the Graham matrix and then take its inverse, sometimes there can be ill conditioning, though you might want to impose positive definiteness and endow it with good properties, depending upon how your data points are, etc., this may be ill conditioned. So because of which we would want to come up with an approximation to this optimal solution, that is to the regularization problem, so that we approximate the solution in a lower dimensional space where we can solve this problem. Okay. So let us go forward with this. Now my phi of x for all these points I equals 1 to M1 is a new set of basis functions, and of course it is a basis function, therefore it has to be linearly independent, right. We choose phi I of x to be g of x minus T I, where I goes from 1 to M1. So you just have to notice this change, observe this. Observe this detail that we do not have capital N units, but we have M1 units, right. This is at centers T I equals to x I. For some I equals for some choice that I have here, I equals 1 to M1. Now my f star of x is summation I equals 1 to m1 w suffix I g of norm x minus T I where T i's have to be determined. Right, because if I choose T I to be x I, then there is the original problem. If T I equals x I for I equals 1 to capital N, it is my original problem, but I do not want that. I want to restrict my solution for I equals 1 to m1. So, let us see how we can formulate the functional. So, we will formulate the Tikhonov functional as follows: E of f star is summation I equals 1 to capital N d suffix I minus summation. So, so this f that my approximation is over m1 units. So, this is where my inner summation has j equals 1 to m1 w suffix j Green's function acting on xi minus tj, right, this squared subject to the regulatory conditions where a differential operator acts on this function f star. Now, this first term here, this can be expanded as a Euclidean norm of 2 vectors, and this can be given by d minus g times w, right. D is a vector here, w is a vector, and g is your matrix. So, let me define these variables what they are. Where we just look into this equation here, where d equals d1 d2 so on to d suffix n, this is a column vector, and w is my vector of all these weights. Just observe this detail here. Because it is over m1 units and not the original n units, and my matrix G is this Gram matrix, which is Gx1 T1 dot dot till Gx1 Tm1 . So, the last element in this array is Gxn Tm1, and to complete this row I have Gxn comma T1. Okay. So, it has n rows and m1 columns, it is an n by m1 matrix. D is my n by 1 column vector and W is my m1 cross 1 column vector. Now, G is n by m1 dimensions, or size and it is no longer sort of symmetric, it is not a square matrix, it is a rectangular matrix, right. So, similarly, if I do this computation on d f star, so I would say evaluating the norm of d times f star, that is the differential operator d acting on the approximating function. This is nothing but the inner product of d with f star times d with f star, the adjoint, right, in the space H where this inner product is defined, and I can simplify this to be summation I equals 1 to m1 w suffix I, this Green's function g with arguments x and ti times this d tilde adjoint operator times d times summation I equals 1 to m1 w suffix I g of x with ti. And you can interpret this as a quadratic form which is w transposed g naught times w, where I will define what this matrix g naught is, and g naught is this matrix which is a square matrix comprising of points which are evaluated at t suffix I, t suffix j, right. This is our Gram matrix. And this is square. So, now we have sort of two terms here which we have expanded in matrix form. The regulatory constraints corresponds to this quadratic form which is w transpose g naught times w, and your approximation error can be expanded as the Euclidean norm of d minus GW. So, minimize this Tikhonov functional which minimizes Euclidean norm subject to this regulatory conditions. So, I will leave this sort of an exercise. The minimization of this Tikhonov functional E of f star with respect to the weights W yields the solution G transpose G plus lambda times G naught times this weight vector W is G transposed D. When lambda tends to 0, W is basically the pseudo inverse or the minimum norm solution to the overdetermined least square solution for the data fitting problem where M1 is less than n, right. So, I will leave this as a homework exercise. So, this involves matrix calculus. Is a straightforward. You can look into my video lectures on matrix calculus. I have about 25 minutes or 30 minutes of video lecture in my mathematical methods and techniques for signal processing course, where I talk about how I can differentiate a scalar with respect to a vector, a matrix with respect to a vector, etc. So, these matrix matrix calculus operations you can straightforwardly do when you express this functional in matrix form. So, once you do that, it is straightforward. I have written down the solution here. So, given how we have defined these matrices G, G naught and our vectors W and D, you can do the calculus and then arrive at the optimum solution. But what is important, I think, to note is the conclusions from this. Right. So, if lambda heads to 0, that is no regularization, then my W is basically G transposed G inverse of this times G transposed this vector D, which is nothing but the minimum norm solution or the pseudo inverse to the least squares problem. That occurs when M1 is less than n, right. We are sort of doing some data fitting here and we want an approximate solution to this, and under that conditions this boils down to the minimum norm solution, and that is what we have here. And depending upon my lambda, I would waive this by lambda times G naught, and that is the regularization effect that I have towards my solution to the weight vector W. Okay, so this is sort of an interpretation here. Sometimes data itself can be weighed. For example, when we deal with PCA, we require covariance matrices. So, the data vectors in a multivariate distribution or density would be could be scaled by these covariance matrices, and these covariance matrices sort of act as weight to these data vectors in the probabilistic sense. Similarly, you may want to weigh data points through a weighing function, right. You do not treat all data points to be the same, you give certain weight, and that depends on the problem. Maybe some cluster of points you may want to have more weightage than the other in your cost, and that depends on the problem at hand. Now, let us see how we can set this up where we have to weigh data points. So, I can have a norm I can define a weighing function, that means data points x can be weighed by a weighing function which is C, and we assume that that to be some matrix, and written in this form norm of x, I will put C here, norm of x c square is given by c times x transposed times c times x, and written in quadratic form this is going to be x transposed c transposed times c x, where this matrix C transposed times C is an M naught by M naught norm weighing matrix. Right, I assume my data vector x is M naught by 1. So, if you assume this to be of dimensions M naught by 1, then this makes sense. Right. Another example. So before we get into another example, so I just would like to write the approximating function f star of x is now summation I equals 1 to m1 w suffix I g of x minus ti, where this norm is this weighted norm. Okay. So, if I weigh the data points, I get a weighted norm, and my approximating function can be expressed in terms of the weighted norm of the data points, and the Green's function will have the weighted norm of the data points instead of just the norm of the data point, right. So, this is one example. There is a more familiar example which is based on the Gaussian case. For the Gaussian case, we can have Green's function over these weighted norm of data points, and this can be written in the form exponential. You have x minus ti transposed times sigma inverse times x minus ti, right, and this is the familiar covariance matrix. That is how our distribution is written. And in the weighing sense, we can say the sigma inverse is sort of written like C transposed times C, the way I described earlier. So, now we can, with these forms that we have, that is by doing the weighted norm on the data points, we set up our Tikhonov functional, and then once we form the the functional in terms of matrices and vectors, we do straightforward matrix calculus on the functional to get the optimum weight vector, right. This is a small detail. So, first setting up the Tikhonov functional in the original form with regulatory conditions, and because we have this overfitting problem, or we just want to have fewer number of parameters with which we can approximate this regularized solution. So, for that we further approximate our optimum solution to yield a suboptimum solution, for which we follow this path. Okay. So, this sort of completes our discussions on Green's functions and neural networks that are based on regularized Green's functions, and further optimizations that we can think of based upon giving a weighing matrix to the data, right. At this stage you may question, how do I determine the centers T suffix I? So, there are two aspects to this. One, you may have an external clustering procedure which is driven by some other optimum condition to solve for your optimum centers, or you set up the optimization conditions over these T suffix i's, and then you come up with equations and then you solve for these equations based on the optimality conditions, so that you want to drive this you want to minimize the functional, the cost associated with the functional. Okay. So, these are two practical ways. So, whether you do it adaptively and then solve for the centers, or use some other algorithm to arrive at clusters T suffix I, these Ti's separately and then plug this, I think this is again a choice in the way you approach the algorithmics, and that is subjective. Okay. So, whichever route you are comfortable, I think the general framework of how we approach this problem by bringing in regulatory conditions is very important, and I hope you will find this useful in your research or your graduate study.